see the title and the authors, let me start by giving 2 comments. In the program, there are 3 authors for this paper, and that's not correct. There are only 2. That's the origin of the error was a computer software problem, and it's very difficult to correct computer problems. About the title, I think part of it, some examples, that's quite clear. I will give 2 examples. Non-statistical systems, maybe I should comment on that. My point of view is that the systems I will consider are not of a statistical nature, only the data analysis is statistical. And that point of view is a little bit controversial because many colleagues in physics believe, and my examples are from quantum mechanics, believe that quantum mechanics is a probabilistic theory. So it should be clear from my point of view, the quantum system is not probabilistic. Only the data analysis will use statistics, and I will show how that will work. I'm trying to find the button. Yeah. So just 4 sections. First, the abstract setting in which I will work. Then the first example is a very well-known and very simple example. And the second one is split up in 2 pieces. Something about quantum measurements, and then something which is rather new, but already deserved a Nobel Prize. I have it mentioned here as weak measurements in quantum mechanics. This button? Yeah, no, the other one. Okay, I don't think I have to recall this too much. Kullback-Leibler divergence between 2 probability distributions, relative entropy in statistical physics, and the Fisher information matrix. And the only thing I need here is that the Fisher information matrix can be obtained from the Kullback-Leibler divergence by taking 2 derivatives. And the reason why I need it is because of the remark that the formula there is also valid when the first of the 2 arguments, the probability distribution P, is arbitrary, does not belong to the manifold M, while the manifold, the parameters theta are the parameterization of points in the manifold. It's a straightforward calculation to show that P doesn't matter too much. And the obvious reason is that at the end you put P equal to P theta, so it doesn't matter too much. That allows me to introduce a slightly extended definition of a Fisher information matrix, not in a point of the manifold, but for an arbitrary probability distribution P, by using the same formula, but changing slightly. First of all, the argument. I hope it is working. Yeah. The argument now is an arbitrary probability distribution, and here the evaluation at the end has to fix the value of theta. Okay? And the set f theta here is what I call a fiber. It's the set of all probability distributions P, which are best fitted by the same P theta. So I have 1 point on the manifold. There are a lot of P's which will give the same P theta. And that's the point where I evaluate this second derivative. Okay? And now I have a notion of Fisher information for arbitrary P. And that's my starting point. So let me first show that on a drawing. I have a manifold. That's the model manifold, and points in it are parameterized with theta. parameters, and I have an arbitrary P, I look for the point in the manifold which minimizes the divergence, okay? And then now I have Fisher information for the point P. And the Fisher information is a second derivative if I make small changes here of this point in the manifold. And that makes that immediately the Fisher information matrix gives an indication, or the inverse of the matrix gives an indication how well the parameters theta are determined by my experimental data, which is that arbitrary P, okay? So that's now the setting, which you can generalize, and that's what I have on the next slide. But first of all, my definition is a covariant definition. It does not depend on the choice of parameters in the manifold. And second property, if the members of the manifold belong to the exponential family, if the model is a model of exponential family, then the Fisher information matrix is constant along that fiber f of theta. That's in fact what I presented 2 years ago at the conference here, and that's the reference for that. In the meantime, my coworker Ben Anthonis has written a PhD thesis, and if you are interested and if you want more details, you can find the thesis on the archive. Okay, that's for the abstract setting. So my abstract setting is the simple observation that I don't need that P or P theta are probability distributions. All I need is some space X of possible outcomes of an experiment, and I need a manifold of model points. So each point in the manifold is a possible realization of the model which I have in mind and which I try to fit to the experimental data. And then, of course, essential is that I'm minimizing a divergence function, which is a map from x times m into the positive non-negative integers. Then I immediately, instead of developing the theory, for that you can have a look in the thesis, I will immediately go to the two examples. The first one is a very simple one, well known in physics. It's the free Bose gas in the grand canonical ensemble. So I have, as known feature of the model, energy levels, epsilon 1, epsilon 2, and so on an energy scale. And my example is a gas of photons. In each energy level, there can be a number of photons, a number of particles. And that number is called little n, n1 photons in the first level, n2 photons in the second level, and so on. And then I do a hypothetical experiment, and the result of the experiment is a sequence of numbers, n1, n2, and so on, okay? But the total number of photons in such a photon gas, you don't know it in advance. Of course, you know it if you do the experiment. You just sum the little n's to get the total number of photons. And then the standard trick is to define probabilities by dividing by the total number of photons. But that's the trick I don't want to do because I don't need a probability distribution. And one reason to avoid it is because it's in fact not very natural. It's of course correct that given the fact that I have total n photons, I have probability P1 to find them a given photon in the first level, but that's irrelevant because in fact total n I didn't know in advance. It's only part of my result. The alternative could be to work with empirical measures, which are measures on the space of all finite sequences, and that gets very technically involved, so that I don't want to do neither. So that's my question: why don't you take directly as the space X of observations just all finite sequences of numbers? Okay, that's what I will do, and then I need a model. Well, the model in physics is always the same. It's an exponential family model with two parameters in this case. That's why it's called grand canonical ensemble. My parameters are beta and mu. Known are the energy levels that are known numbers. And so the probability distribution of getting a sequence of n's is the one here. And I assume that the normalization is convergent, which depends on the choice of the epsilons. The parameters have a limited range, but that's, okay, all quite trivial. Important is now that I need a divergence function, and instead of taking Kullback-Leibler with two probability distributions, I still have one probability distribution, which is the model point, but now directly I put here the numbers n which come out of the experiment. Okay, and you can show that this divergence function has nice properties, and of course what I want is that this choice reproduces what is known in all textbooks of physics, and that's indeed what happens. I will not go into details, but you get standard results by minimizing the divergence function given the knowledge of the outcome of the experiment. You can go further. You can calculate a metric tensor. You can calculate the extended Fisher information, which then, of course, is constant on a fiber of all sequences n which are projected in the same point of the manifold. You can even go further, and that you can find in the thesis. You can introduce covariant derivatives, and there is a method described in the thesis how you calculate connection coefficients for them. But I will stop here this example and go to the next one, which is measurements in quantum mechanics. And now, I will not work with probability distribution, and the main reason is that in quantum mechanics, you have an analog instead of probability distributions. You have density matrices, and what axioms of quantum mechanics say is that the actual state of a quantum system is some wave function, psi, and the projection operator, the rank 1 projection operator onto that wave function is the actual state of the system. However, yeah, that's the definition simply. However, if you do a quantum experiment, and that's something which I think there's agreement on in the physics community, if you do a quantum experiment trying to measure the wave function, you don't get what you want. You don't get this matrix. You only get the diagonal part of it. And diagonal part in a basis, and the choice of basis is dictated by your experimental setup. And you can change your experiment, and then you get the same matrix in another basis, but you never get the full matrix at once. You only get the partial information. And the way I see this is that my experiment puts a condition on what I can get out about physical reality. So I consider this result, which diagonal part of the matrix, I consider this as a conditional probability distribution, or the equivalent of that. Okay, because it's a matrix, of course. But the eigenvalues of that matrix, the diagonal elements, then can be interpreted as probabilities. Only these are conditional probabilities. They are conditioned by the way the experiment has been done. So my example is the most simple one, a wave function with only two complex components. Then if that's the state of the system, I get the typical, what one calls then an entangled state, which is the matrix with all ones here. And if I do a measurement in the obvious basis of 1, 0, and 0, 1, then of course I only get the diagonal elements, and there are two zeros here. Okay? So it's an axiom, and I think everyone accepts it, although it's maybe a little bit too strong. But the result of a quantum measurement is always such a diagonal matrix. And now what I change here, it's always a conditional expectation. It's conditioned by the fact that it has to be diagonal in the given basis. Okay? Okay, let me now go to the mathematics. The book of Petz and the work of Petz has been mentioned already 2 days ago in the conference here. It's a very interesting book, and in that book you find a definition of what is a quantum conditional expectation. Okay? And the reason why I need it is that the map from the initial state of the system to the diagonal part is indeed an example of what Petz calls a quantum conditional expectation. Okay. So that's the mathematical context of that. And the mathematics behind that is quite deep going. It originated with work of Accardi and Cecchini, and it relies on Tomita-Takezaki theory. And those who know that theory, it's very deep going and has led to a lot of mathematics. It's one of the main results of mathematics in the 20th century. Classification of von Neumann algebras and all things like that all started with the work of Tomita, somewhere in the 60s, I think. But I will not talk about that mathematics. I will only use a theorem which is found in the book of Petz. So let me continue with the example. What I have is, and now I change a little bit notation, my matrix, which was before psi, projection on psi. I have to go quick, but I only have, well, maybe I skipped the last part, which is the most interesting one. I have experimentally density matrix, which comes out of, which is the state of the system. Only the diagonal part is what I measure. It's in this manifold of diagonal matrices. My model, I assume, is a subpart of it. And then a theorem of Petz says that the Pythagorean relation holds, that the standard Kullback-Leibler divergence for density matrices holds, which means that if I minimize the distance between rho and sigma c, or between rho and sigma, it gives the same result, because this here, of course, does not depend on, I'm sorry, this last one, okay. I'm a little bit confused, but let me go on. So instead of minimizing the distance from sigma to rho, I only have to minimize the distance from the diagonal part to rho, and that's what the people do in practice, because you don't have anything more than that. Okay, then a few minutes about weak measurements. What's the problem of quantum measurements? Well, it's clear. They are incomplete. You only get the diagonal part. The reason for that is that quantum effects are seen on very small systems, like a single photon or single electron or something like that. And usually the measurement destroys the state of the system. That's what one calls collapse of the wave function. The measurement itself is enough to destroy whatever state the system had. Recent experiments overcome this difficulty, and that's what is called weak measurements. Well, the name comes from a paper, 1988, and the paper itself is not universally accepted. But my point, and without going to details, the interpretation we make of that is that what happens that you can explain it in terms of conditional expectations, and that one assumes a model now which does not consist of diagonal matrices, but corresponds with a model of diagonal matrices. And so what one measures is then a point here, which approximates, minimizes the divergence in here, but in such a way that in fact one obtains information and that this row minimizes that sigma. And the reason why we believe, at least that's a conjecture, we believe that the reason why one can do such very delicate experiments is that there's an amplification effect, because experiments are made in such a way that this diagonal part here is at the border of the manifold of all strictly positive density matrices, and at the border the Kullback-Leibler divergence is almost divergent and becomes very sensitive to small changes in the initial state. And I will stop here. Thank you for the... So from sigma to sigma c, the equivalence is you have your experimental data and you fit an element of your manifold. Yeah, and you mean this one? Or no, you mean the right one? This one here. Now from rho c to sigma c. Yeah, but the data is this here, and you project onto the manifold of your model points. And so this is the real state of the system, which you cannot, you don't know it. It's unobservable. Experiment only shows you the diagonal part of that matrix. So there is no classical counterpart of that.